Among all organic molecules that exist on Earth, the most common ones are carbohydrates. In the early 19th century, it was determined that natural substances such as glucose, sugar, starch, and others have formulae that show the presence of carbon and water. Carbohydrates. This group of compounds was named in this way by the chemist Carl Schmitt. In nature, carbohydrates are produced from carbon dioxide during photosynthesis, a process that takes place in green plants under the exposure to sunlight. In 1861, the Russian scientist Alexander Butlerov was first to synthesize a sugar-like compound similar to carbohydrates found in nature from methanol. Carbohydrates in nature are widely represented in the structures of plants and other living organisms in the form of both monomers and polymers. Around 100 years ago, the nature of simple sugars was explained using Butlerov's theory of chemical composition. Monosaccharides are presented as oxycarbonyl compounds. However, the formula for an aldehyde does not reveal all the properties of monosaccharides. Investigations have shown that in contrast to methanol, whose infrared spectrum shows a carbonyl group absorbance, in the infrared spectra of glucose and other monosaccharides, these carbonyl group absorbance peaks are absent. It turns out that monosaccharides exist both in aldehyde and hemiacetal form. A molecule of glucose contains asymmetric carbon atoms. The presence of these carbon atoms results in the existence of stereoisomer pairs, which differ from each other just like an object differs from its mirror image. The difference in optical antipodes can be illustrated by opposite rotation of an object and its mirror image. For the general representation of optical isomers, we use Fisher's projections. In glucose's aldehyde formula, there are 4 asymmetric atoms. Apart from glucose, there are another 15 hexose stereoisomers. For example, this is how D-glucose differs from L-glucose. These are optical mirror antipodes. By changing the configuration of carbon number 2, D-glucose becomes D-mannose. Glucose and mannose are a pair of diastereomers. The fifth asymmetric carbon arises upon the formation of a cyclic hemiacetal, and this forms two new stereoisomers, alpha and beta anomers. Nowadays, three-dimensional representations of monosaccharides are often used. The ring is perpendicular to the plane of the diagram. The substituents are located below and above the ring. This structure, just like any other one, tends to occupy the most stable conformation. The pyranose ring of glucose, therefore, takes on the shape of a couch. This is the most stable conformation where there is the maximal number of equatorially distributed substituents. Crystallized monosaccharides exist only in the form of cyclic hemiacetals. The anomers have different optical activities. However, in monosaccharide solutions, the angle of optical rotation changes with time. Alpha-glucopyranose's angle decreases, but increases for the beta anomer. This happens as a result of tautomerization. In a solution of glucose, an equilibrium between both hemiacetal forms is reached. Tautomerization and the presence of several functional groups make monosaccharides reactive compounds. In Tollins's reagent, the aldehyde group of monosaccharides gets oxidized just like in simple aldehydes. The silver metal that gets produced during the reaction forms a layer on the inside of the test tube. When a monosaccharide interacts with dilute nitric acid, both the aldehyde and primary alcohol group of the monosaccharide get oxidized. Upon the reduction of xylose, the aldehyde group becomes an alcohol group. The result is a polyatomic alcohol called xylite. This is a product that is sometimes used as a sweetener. Likewise, when glucose is reduced, the product is the polyatomic alcohol called sorbite, which is used in confectionery goods as a sugar replacement for diabetics. When monosaccharides react with ethanol, only the hemiacetal hydroxyl can easily interact. The product is glycoside. Glycosides are very common in nature. They are very significant in biology and have medicinal uses as well. Lil extract's active component is a glycoside. When glucose reacts with phenylhydrazine, it is the first and second carbon atoms which take part in the reaction. The product is an ozosone.